Record. Okay, so welcome everybody. So we're recording here. We're going to talk about polar graphs. Yesterday we talked about polar coordinates. Again, you can have these printed out from It's Learning, or you can just kind of write down on a scrap piece of paper. And you can even do some of the sketches as well on a piece of paper as well. The other thing you do is you need a graphing calculator right now, so go and grab it if you don't have it. So as you're grabbing that, just reviewing from yesterday, converting between polar and rectangular coordinates. There's two ways that we've discussed. Identifying how to plot that point, and it's either through rectangular coordinates with some x direction and some y direction, or lengths, I should say, in the x and y direction, or, so I could call that xy, or I could call it r theta, with some angle and the length of the radius. Sometimes I actually don't know if this R stands for radius, because it's obviously a part of some concentric circles that we looked at yesterday. It's the radius of a circle, or is it also like the resultant of when we think about our components of our vectors, like we did back in physics? That's actually a good question. So again, converting between x and y and r's and thetas. So x is equal to r cos theta. Y is equal to r sine theta. That's just like your physics components. And in terms of Pythagorean theorem, to get you what r is, and an inverse tangent of y over x to get you what theta is. So we have ways of solving for x and y in terms of r and theta, and r and theta in terms of x's and y's. And we'll need that in a minute or two. So, okay, so we converted points. What about converting a whole bunch of points? Like in an equation. Like, so if I have y equals 2x plus 1, that's the equation of a line in rectangular form, but what is it in polar form? Well, the main thing I got to do is just change all my x's and y's to r's and thetas. So I go up to my conversions and see, okay, what is x and y in terms of r and theta? Well, y is equal to r sine of theta. So I'm just going to substitute y with r sine of theta. And then 2 times x, well, what is x? X is r cosine of theta. And technically that's it. But it's not, it's written implicitly. Everything's all kind of jumbled up. Let's see if we can write it explicitly. And the variable that we're probably going to want to solve for in these, which seems a little backwards, because usually we try to solve for the dependent variable, theta would be the dependent variable. This time we're going to usually, when we write things in polar form, we solve for the independent variable, which is r. So I'm going to subtract and get the terms with an r on one side. I've got to keep my eyes on if anybody pops in the room here. And I'm going to factor out an r. Oops, and I think I messed up. This should be equal to 1. Sorry. Equals 1, so equals 1. And then to solve for r is simply and that would be my equation. So that is the equation of that line. Now there's actually a little bit more to it, and we'll get to it in a minute in terms of what is theta. So theta will have to have some kind of an interval in order to graph this. And we'll take a look at that. Maybe we'll come back to this one in a minute to see what we might have to set theta to be. But in general, this would give you the shape of that graph, or at least portions of that graph. Especially if I let theta be all values between negative infinity and infinity. All right, so how about this thing? So x squared plus y squared equals 9. So, all right, x is r cos theta, so that's going to be r squared cosine squared, because I'm squaring both of those terms. And y squared, well, I'm just going to square that, so that's r squared sine squared equals 9. And again, I'd probably like to solve for r, so let's maybe factor out an r squared. Now, I'm only doing a couple of these with you. Usually in a normal course, we'd spend a bunch of time looking at a bunch of different ones of these. And anybody see anything interesting there that we recognize and can simplify? Now, cosine squared plus sine squared is always equal to
1.
1, right? So therefore, r squared is 9. So therefore, r is 3. Now, technically, it's plus or minus 3. But remember what that plus or minus does when I'm talking about radii. When we were looking at things yesterday, here would, if I'm plotting this point, this would be a positive r value. But then if I had this angle and coming around in the opposite direction, that would be a negative r value. So I can, again, what I would have to do is to say, okay, I'm going to have this, but I'm going to let theta be all the angles between negative infinity or maybe something like, in this case, I know I'm going to say from 0 to 2 pi, because this is, do we know what x squared plus y squared equals 9 looks like? What's that the shape of?
Circle with a radius of 3.
It is, and if you look in in polar form, r equals 3 just means I don't care what the angle is because it's not angle dependent, just let the radius be 3. So at every single angle that I go around, I'm going to go out 3 units. So you can see right now how incredibly simple it is to do graphs like circles and circular types of graphs in polar form, because the equations are so simplistic, you don't get into the error of being non-functions. Remember, for a function test, it's got to pass a vertical line test. Circles are not functions in the rectangular coordinate plane. But in the polar coordinate plane, they are considered polar functions. So because we'd be making our line out from the origin. So super simple. And in fact, I'll show you in a minute, your calculator really likes to do, can very easily do circles in polar coordinate form. And we'll get to our calculator in a minute. All right, so how about y equals 1? Just a flat line, which seems kind of weird now that we say that polar form really is a good job of graphing circles and stuff. Let's see what this is going to wind up looking like. Okay, so y is simply r sine of theta equals 1. And that seems simple. So r equals 1 over sine of theta, or r equals cosecant of theta. Well, that's interesting. So it's just this simple horizontal constant function is this function of cosecant of theta. Now remember, these are giving me r values. So there are values that are coming out from the center of the radii. Again, in a minute, we're going to look at graphs. Remember, that would be coming out from that central graph. That would be giving me that shape. Well, let's pause real quick and maybe let's take a look at what our calculator is doing here. So let's turn our calculator on. And so I'm going to kind of give away the magic here. In fact, in a minute, we're going to kind of work a little backwards. So the first thing you want to do is to change your calculator. Make sure it's in radian mode when we're in polar. And you want to come down and change to polar mode. If you have an older calculator, it'll say, I think it'll say POL. So our 4 functions of our calculator, or our 4 modes, are functions, parametric, polar, and sequential. So now that we've got it in polar mode, if I go to my y equals, it's not a y equals anymore. It's now an r equals. So it's waiting for me to solve in terms of r. So let's do this last one. R equals cosecant. Well, I don't have a cosecant button, but I can do 1 over sine. And now before I hit graph, there is something I want to check. I want to go to my Windows setting, and look, the Windows setting has a little bit of extra stuff now. In the Windows setting, it now has this dependent variable of theta. So right now I've got it set from going from 0. You can see mine is in terms of 2 pi, but if it's not 6.28, just type in 2 pi. Because that at least does one full swipe around this polar curve. My calculator, there we go. So now at least, and my step, it means how often I'm going to be making my little marks or plotting points. Right now it's at 0.13 radians. I would say in general, in terms of radians, like something like 0.1 is good. If you have a theta step that's 1 or 1 radian, you are only going to get about 6 plotted points as it goes around the polar coordinate plane. So 0.1's a pretty nice one. So let's kind of see what happens. And there it is. There's my flat line. And if you trace it, if you hit the trace button and kind of arrow to the right, that'll increase theta. And you can actually watch how it's graphing. It kind of slows down and then speeds up again. And it looks like then it starts to repeat itself over and over and over again. So maybe we didn't need to go all the way from 0 to 2 pi to graph all of this. So it could have had a much more restricted domain, but at least we get the shape of the graph. Again, we could spend a lot more time looking at that. How about the super simple one? R equals 3. Let's see how good it is graphing a circle. Look at that, full circle. Well, almost, because the calculator, because of its pixel issue, I think came up short there. Did I say from 0? Yeah, I put in 2 pi. What was 2 pi? Why didn't it give me the whole? Yeah, sometimes it just won't finish that off in the end. But much better than rectangular form, because otherwise I'd have to do the upper half and then the lower half. And how about this last crazy thing here? How about 1 divided by sine theta minus 2 cos theta? Oh, by the way, notice that when I'm hitting this variable button, this x button, it's putting in a theta for me because it knows I'm in polar mode. Again, the xt, theta, n correspond to the 4 modes of your calculator: function, parametric, polar, and sequential. So I did do that right. My whole denominator's in parentheses. And what were we supposed to get? This was supposed to be this linear function. Let's see how that turned out. So you can see, even if you watched how it was graphing, it kind of started right here, then went in that direction, and then finished the graph in the other direction. Remember, what it's really doing is kind of going around the unit, I'm calling it the unit circle, going around the circle in the polar coordinate plane and plotting those points. It might give you some points that are down here first and over here second, because it's generating them through sinusoidal curves. So keep your eye on it. Sometimes it's kind of interesting how it's graphing, and we'll see that in a minute too. Okay, so there's a little sneak peek at your calculator's ability to graph in polar curves. And again, circular things are super simple in polar mode. How about going backwards? So if r equals 2, the question is, what is it in terms of x and y's? Well, what does r equal? Well, r technically equals the square root of x squared plus y squared. And you could do that, but after you do these a couple times, you're going to wind up seeing a little shortcut that at this point I probably want to square both sides just to get rid of that big square root. And hopefully you recognize, just like Danny did earlier, that this is the standard form of an equation of a circle centered at 0, 0 with a radius of 2. Well, obviously we saw that a second ago. What sometimes you might want to do is that if you say r equals 2, you could then say that r squared must be equal to 4, and then just replace r squared with x squared plus y squared, and you would get that automatically. So that's one way to do that. All right, so how about one that's got a couple different things? I've got an r and a sine of theta. So let me give you a suggestion here, that what I'm going to suggest you do is I'm going to leave the r alone just for a second, and I'm going to change the sine in terms of x's and y's. Well, what does sine equal? Well, sine equals y over r. So now that completely didn't get everything in terms of x's and y's, because I still have these r's, but I've got an r here, I've got an r here. If I multiply both sides by r, I now get an r squared equals 8y. And I like r squared because then I don't have to deal with that square root. So I get x squared plus y squared equals 8y. And I'm going to be happy with that. Just like I was happy with this last one, that I'm not solving these explicitly because sometimes they can get a little bit difficult. In fact, at this one, if I actually wanted to see what was going on, I wouldn't solve it explicitly, but I could do a little bit of completing the square to kind of see what was going on in that graph. In fact, anybody know what this graph is? This is not a circle. So what this is, and I'm still in polar mode, I'm going to put it in 8 sine theta. It might be a little hard to see. Change my window, my WiMAX to something bigger. Yeah, it's a little distorted now because I changed the dimensions, but this is an equation of an ellipse. This is a circle, but that's been kind of stretched out more in the y direction than it has in the x direction. So it's a little bit oblong. And then one more here. So again, I like to leave that r alone because I see this other trig function. Sine, once again, is y over r. I'm going to multiply everything through by r, just to kind of, so I'm really kind of avoiding those square roots. And now I don't think I can avoid it. R squared is x squared plus y squared. R is the square root of x squared plus y squared plus 2y. Boy, that is pretty darn ugly. That's pretty ugly to be whatever this thing is, 1 plus 2 sine theta. Let's see what this looks like. Ooh, look at that. That is pretty cool looking. You're seeing your first example of a limacon. A limacon is this kind of, it's created basically with another shape. It's called a cardioid. This kind of basic shape all around is a heart shape, and we'll talk about names of shapes in here in a second. But this is coming all the way around and then looping back through. If you trace through this, here's, let me start out at 0 again. Starts here at 0 and traces, comes around. I'm increasing theta, comes around and kind of like does the super duper looper. It kind of loops through and then comes back out again. And notice, look where I am at 6.2. That's about 6.28. I finished my complete cycle all the way around back to 2 pi radians. We'll talk tomorrow about how we're going to calculate areas inside of here. That's where the calculus comes in. So right now we're still kind of doing pre-calculus stuff. This is no calculus here just yet. So what I'm going to do here is maybe I'm going to start this, but I'll let you maybe finish it because I've kind of given it away a little bit of how to actually graph these and what these looks like. What I'm going to suggest is to maybe graph 8 sine of theta by plotting points. And this is something that we would normally do in class to kind of get a sense of what it looks like. So you would then take, I can kind of quit and make sure, now I'm doing these in degrees, so I got to switch over me into degrees. I'll do a couple here. Now I'm just going to do 8 sine of, oops, 8 sine of 0. Well, obviously I should have known that, sine of 0 is 0. 8 sine of 15. Now I'm in degrees, so it's going to give me degrees. So 2 point, let's say 1. And I'm going to stop here and let's plot those 2 points right now. So at 0 degrees, I have a radius of 0. Well, obviously that's right here. 15 degrees, I'm going to have a radius of 2.1. Now I'll say that each concentric circle is 2 units in length. Now again, if you don't have this printed out, just make a quick coordinate axes and put a couple circles. You're going to need at least 8 circles around, because that's eventually what this is going to give you, a big radius of 8. So I'm going to go out 1, 2.1, but whoops, up on the 15 degree mark. So I came up 15 degrees and out 2.1. I'm going to do 8 sine of 30. Ooh, that's a nice pretty number. So that's 4. That was 8 sine of 30. Calculator up here. So at 30 degrees, I'm going to come out 1, 2, 3, 4 radii. And I'm just going to keep going. Now, if you were smart about it, there's 5 point, let's say 7. So 45 degrees, I'm out 1, 2, 3, 4, 5.7. Isn't there a quicker way for me to do this? Yes. Obviously, I could just punch this in polar mode. But I can also create a table. I'm going to go up and set my table at 0. I'm going to change the table every 15 degrees. I did this earlier before I started here. And then I can just jump over and grab the table. And why is that? Oops, it's because it doesn't have my function in it. I want to put my function in, 8 sine of theta. So there's my function in, 8 sine of theta. Had my table set to go from 0 and after 15 degrees because I'm in degree mode. And then now I should have those values that I just saw. So I can go and do a couple more, like 6.9, I'll say that's 7. So 60 degrees, I'm out at 5, 6, 7. Let me just get a couple more. 7.7, so 7.7. And lastly at 90 degrees, that's sine of 90 is 1, so times 8 is 8. So right now I can kind of see that I have this shape coming around this direction. And not only that, but we also sometimes indicate, just like in parametric equations, we indicate the orientation, that it's going counterclockwise as theta increases. We always measure increasing theta values, but the graph could obviously be going backwards. Well, I'm going to say, just for time's sake, just keep going, play along, and see how long it does take. In fact, I'm just going to take a sneak peek. When does it get back to 0? Oh, right there at 180 degrees. By the time I get to 180 degrees, I think I'm going to have finished and plotted the other half of this and seeing what this graph looks like. Now, this was my 8 sine of theta graph. That's this one, which was not a circle. This didn't turn out to be a circle, so it's a little bit wider in the y direction than it is wider in the x direction. This is going up 8 units, but we can kind of see that it doesn't look like it's going 8 units in the other direction as well. So sometimes to create shapes, it doesn't take a full 2 pi radians to get all the way around like we normally think of with a circle. And that's because some of these other coefficients that are being added into these equations. So normal times we would have plotted a couple of these, maybe 1 or 2 of these by hand and kind of see what was happening. But obviously we now have our graphing calculator. So let's finish out here and just look at what our graphing calculator is graphing here. We'll talk about some of the names of these shapes and try to get a pretty good graph. So I want to graph r equals 2 cosine 3 theta. So I'm going to go back in. Now the thing is here is that I want to make sure I am in radian mode when I'm graphing, because I don't want a unit when I'm graphing. I want everything to be unitless. So it's in radians. I'm putting in, what is it, 2 cos 3 theta, 2 cos 3 theta, and I'm going to go back to maybe do a zoom 6. Oop, too small. Let me do a zoom 4. Well, that's kind of cool, but it happens so fast. Let me see if I can get it to slow down a little bit. To get it to slow down, you can just make your theta step smaller, because then it's going to be plotting a lot more points, and it might go a little bit. Oh, yeah, that's way too slow. Stop. All right, that was way too slow. Let me delete 1, 0. Now it's coming around. Now slowly coming around, and you can see it tracing itself through this graph. Now again, that would be, it would literally be, you would be plotting points going around and sketching that graph. So what you're seeing is your first example of a rose curve. These are called rose curves because they look like a flower. So, and it looks like it started out, and it looks like 2 units out, if I can look at my scale here, which makes sense because this 2 normally constitutes the amplitude of a sinusoidal function, and that's how far it ranges from the center line to the max and the min. So it's going to start out 2 units out, and I'm going to hit trace, and I'm going to trace to the right and just kind of see, okay, it looks like it's coming around here. And then, I can fix this and get back to a little bit quicker. I come around, let's go back to 0, trace me around. And then here, you can probably already guess at what angle it's going to be coming down at, because this is going to be broken up into thirds. So it's going to have to be 120 degrees between each one of these different petals. So this is probably going to come down on this 240 axes here, and then come back to the center again, and then probably go out to 2 units on the 120 degrees, and come back to the center again. Just follow up, coming through, and then finishing back out to where I started. Now, how long did it take me to get back to where I started? Look at that. That's interesting. 3.2, well, that's 3.14. That's pi. It only took me pi radians to get back to where I started. It didn't take me 360. But if I put in some of my orientation arrows, kind of following the path through, it went through this path. Knowing the path or the orientation of the graph is going to be important, taking and calculating areas of these curves, which is the calculus in which we'll talk about tomorrow. So there's your rose curve, a 3-petal rose curve with roses of lengths of 1. Well, that's 2. Well, that's interesting. This looks like that was the petal length. And maybe this winds up being the number of petals. I don't know. Let's see what happens. This next one looks kind of like it. Nice simple function. 3 sine 2 theta. Ooh. Almost lost my soup cans. Where's my camera? All right. So maybe I'm going to guess that the petal's going to be 3 units in length, and maybe I'll just have 2 petals. Let's see. Again, we would maybe have plotted this. We're normally in school, but for time's sake here. Well, look at that. It's hard to tell, but you can see that this is going to be a length of 3. It's obviously longer than 2, and we could look at some of the coordinates and calculate some of those. In fact, if I hit trace, I would just have to put in probably 45 degrees into here. 45 times 2 is 9. 45 times 2 is 90, sorry. Sine of 90 is 1. 1 times 3, that tells me I'm 3 units out. So it is a petal of 3. But I've got 4 petals this time. Let me go back to where this started. This started at the center, and it goes out 1, 2, 3. So all the way out to 3 and back. So I'm following that. And now where does it go next? It's next going down into the 4th quadrant. So coming down into here, 3 units out and back. And keep going. Where does it go next? Oh, it's looping around here to 225 and back. And we could probably guess that this is going to come back and finish around here and back. Ooh, my petals don't look very symmetric. But this is another rose curve where, again, this is the petal length. But what you have now seen that this is half the number of petals. And if this is an even number, you double the number and get the number of petals. If it's an odd number, that is the number of petals. So if you had 5 theta, you get 5 petals. If you had 3 theta with, 4 theta, then you would have 8 petals. And you can easily do it. Just go in and put in a 4, and now you got 8 petals all the way around. Now again, if they get stuck and you start playing around with these, all you got to do is just make sure your window settings going at least through 1 full cycle, 1 full period from 0 to 2 pi. It might not be the full period of the petal. Remember, some of them only took half of that, pi radians, to kind of get through. So if you're playing around with these, you might have to change that window setting. All right, let's finish up these last 2, see what these crazy things look like. So we've seen 2 rose curves. And what do I got? 2 plus 2 sine theta.
That's going to be a cardioid.
It is a cardioid. Good, Dan. So it's starting, and if you traced it, it started right there at 2. And it looks like it's going 1, 2, 3, up 4, which is going to be a little bit off my screen. But that's okay. I can kind of come around. And it's called a cardioid, obviously, because it looks like kind of like a heart, an upside-down heart. And you can change the orientation of these hearts by changing the trig function. You know, if this was a cosine function, then it's going to be a sideways one because it's going to start out, and it's going to, remember, cosine functions start out at their maximum up at the top of the graph. So the cosine for a cardioid is going to start out at its maximum radius to begin with, going all the way around. And I didn't check, but how many radians does it take to finish this whole thing? Well, it looks like it is taking 6.28. So it does take 2 pi radians to get me around this whole shape. So this is a cardioid. And the last one, let's see what this last one is. 1 plus 2 cos 2 theta. Oh, I forget the name of this shape. This is 3 units out, and it came down, did this little loopy thing down below here. And again, you can just hit trace and arrow to the right, and it'll take you through the path as theta increases. And I have to cheat and look at my next page, because my next page, I think, has it. That's the name of it. So kind of orientating through that shape. That's not a common shape that we wind up seeing on the exam. I think it's a lemniscate. And I'm going to look at my next page here. I think that's what we have here. I know it's really kind of light. It looks better when you're on the, when you have the PDF open. It's this lemniscape, has this kind of like infinity looking symbol. So we have our rose curves and talking about odd petals versus even petals, you know, doubling the number of petals if n is even, n number of petals if n is odd. We just mentioned that. We have cardioid, a simple cardioid, that's this one right here. But then there is a limacon with a loop in the middle, and we saw that earlier, that super duper looper kind of looking shape. And those are interesting. We'll talk about those tomorrow. And then your basic circles, circles that in this case are not centered at the origin. If you wanted a circle that's centered at the origin, you just put r equals whatever your radius is. So, and we have other different, here's 8 petals, 5 petals. The one that's interesting is the spiral of Archimedes, is if you just let r equal theta. That means as theta increases, the radius will increase. So as you're going around, as theta increases going through the path, the radius is going to get longer and longer and longer. And if you zoom out a couple times, and again, notice it stopped. Well, I just need to make this something bigger. I don't know, like 8 pi. And it'll keep kind of going around and around and around and around. So there's your introduction to polar graphs. You can play around with these, and I invite you to. In fact, I might be asking if you come up with a pretty cool picture of some kind of a picture. A lot of times people do rose curves, and they put rose curves on top of rose curves. And if you get a funky picture, take a snap of it, send it to me, and I'll post it and share it, because these are kind of fun to play around with. So again, still pre-calc stuff. We're just graphing stuff, going back and forth between rectangular and polar coordinates, and rectangular and polar curves. Tomorrow we finally get into the calculus of, okay, how do you find the areas of these things? And it's an incredibly, incredibly simple integral that, too bad that we missed, the BC people missed out. This was not on their exam this year. They dropped this topic. So at least now you guys are aware before we head to it next year. So, all right. Have fun with this. I'm going to pause my recording.